Hi, this is Cornelius Gould. I'm a member of the AES Loudness Education website committee. I'm here to present to you an overview of loudness in terms of what we're talking about on this website and in other presentations that we're presenting here to the group. So we're going to jump right in since we have a little bit amount of time and a lot of things to cover from other presenters. And we're going to start by defining what it is we're talking about when we're talking about loudness here. And we're going to be giving just a top level overview. Nothing too deeply here. So if you really want to know and dive in to the exact minutia of the specifications and where they came from, I suggest checking out some resources that I point out here at the bottom of the slide, one of which is the AES 71 standard, where we talk about loudness and loudness control in terms of how it's used in video and a few other sources. Also check out AES TD 1008 and AES 77 standard, which was just released earlier in the year. Those pertain to streaming loudness for audio, as well as the R128 and ITU BS 1770 standards, which are the basis of all of the loudness standards that we're presenting here and recommendations on this presentation. So let's start with what are we talking about when we talk about normalization? Well, when we talk about normalization, the first thing most people think of is the classic peak normalization function. And what peak normalization does is that it scans various files and it'll adjust each file so that the peak level matches from file to file. Now, back before we had much of a loudness war going on with recordings and all of that and lots of mastering tools that were readily in use, this worked fine. But nowadays, albums are processed just as much and in certain cases more than many radio stations, so that you end up with albums that sound louder than the other album. And that's where peak normalization kind of falls apart here. And in this example here, we've got two waveforms, one on the left and one on the right. You can see the one on the right is much thicker and fuller than the one on the left. And these are two songs from two different eras. One on the left is an actual Fleetwood Mac song from the 1970s, and the one on the right is a current track from a top 40 song. Now, these have been peak normalized, so they look like balanced to the eye. To the ear, the file on the right is about 6 dB louder than the one on the left, and maybe even more than that. So this is where peak normalization kind of falls apart, because the files look like they will be even. They look like they should sound the same, but they do not sound anything the same when it comes to loudness. Like I said, the one on the right is about 2 to 3 times louder, maybe even 4 times louder than the one on the left. So the kind of normalization that we're talking about here is loudness normalization, where you scan the files and you match them up to be the same volume level by ear. And when you do that, and you get something like this, where the file on the right, which was really tall and full before, now is a lot smaller than the one on the left. So to the eye, you would think the one on the right sounds quieter than the one on the left, but that's not the case. The one on the right and left sound the same loudness-wise. And this is through the use of specialized RMS-based loudness matching. We're going to get into the basics of this type of normalization here. The first thing we need to decide is how we're going to measure these. And there's all kinds of meters and things out there that we can use for measuring levels and trying to glean some kind of a loudness reference out of them. But we're going to focus on two of the most common ones. One is an older one, and one is a meter that you see all over the place in use in production today. Those meters are the VU meter and the peak meter, or the sample peak meter. We're going to start with the VU meter on the left here, and that is the standard mechanical meter that we've all come to know, especially us old-timers that have been in the business for a while. The idea behind it is to have it kind of match more or less how we perceive loudness, and it does that by having a very specific movement to it, where the needle is designed to have a 300 millisecond rise time and a 300 millisecond fall time, and that kind of gets you something that kind of closely matches how we perceive loudness on the meter. And it's the oldest loudness meter there is in use that I'm aware of, and it's been around for a long time. So that's its strength. It's pretty decent at telling you what the loudness is from track to track. And it's one that many professionals prefer to use to this day because they can get a better feel for how loud different elements in their mix is. So that is its strength. It's kind of easy to tell how loud things are compared when you compare them one to another. Some of the downsides to them are the fact that you can't really tell what your headroom really is because they don't move instantaneously. It's possible that you can use them in a way where you could run out of headroom and get distortion from time to time. I mean, if you're used to using them, you know how to do that and kind of have some room. But for a lot of people, it's kind of hard to really judge where your headroom is and how much headroom you have left when you're doing a mix. The other downside is especially in today's music, if you play music with lots of bass in it, which is a large portion of the music today compared to when these meters were designed, that bass energy can throw the meter off, and it ends up showing a level that's way hotter than you will perceive by ear. So sometimes meter will be slamming, and you're kind of going, well, it's not that loud, but this meter is really pegging off the scale. So that's kind of two of the weak spots to these meters. The other meter is the peak sample meter or the peak level based metering. And it's really good at showing you how much headroom you have left, because when you get to 0, which is at the top of the scale, there's no more room to go and you're going to run out of headroom. So you kind of know where that distortion function is. Makes it kind of easy to understand what you're doing and what your levels are like. And you know that when you hit 0, it's pretty bad. And it's everywhere. So especially in the current generation of producers and radio folks and TV folks, they know that meter. They see it everywhere. Now, the major downside to this meter is that it's basically impossible to determine what the sensational loudness is between two different tracks or more by using this meter. And essentially what this meter is showing you is the same thing that the peak loudness normalization function is doing that was in our first slide in the presentation here. It's showing you where the peaks are, and you're matching the audio based on peaks. So when you're using this meter, you're basically becoming a human version of the peak normalization function. To illustrate this, let's go to our next slide here, which shows the VU meter and the peak sample meter functioning side by side on two tracks that were normalized to minus 24 LUFS. So the one on the left, you see that's the older song, and you see the VU meters kind of bouncing somewhere around -5 or so on the scale. And when you compare it to the normalized version of the track on the right using the VU meters are kind of in the same ballpark between the two. So they're showing you that, yeah, okay, you're basically getting an indication that the loudness is similar. Now, take a look at the bar graph meters, the tall vertical ones to the left and the right. Those are peak meters. And what you see there is that they're showing you literally what you're seeing on the wave files. So the peak meter on the left is showing you a hotter level than the one on the right. If you were to adjust the meters by hand to match each other, what you get is the file on the right would be increased in amplitude to be more like peak normalized, and then you have no loudness matching whatsoever when you do that. What you see here, the VU meter is doing a pretty decent job at showing you what the loudness is, with the exception to the bass issue that we've got going on. So if we can come up with a better way to display what the VU meter is and make it sensitive to how we are perceiving the loudness, that would make a great meter, wouldn't it? So that's kind of where we get into the loudness standards that we're talking about in these presentations here. And the very first thing here that we have in the toolkit for loudness measurement is a system that compensates for how we perceive sound across the spectrum. This is the ISO 226 equal loudness curve diagrams that you've probably seen here and there. It's sort of like an updated version of what us older timers know as the Fletcher-Munson curve, but this has kind of been updated with new research here. So these are the updated curves for how we hear. And on the left of the scale is basically bass frequencies. As we go all the way to the far right, those are some of the higher frequencies that we hear in our spectrum. And what this graph is showing you is how much you have to turn up those frequencies to make them match the line in the middle-ish area, which is the 1,000 hertz reference point. So in order to make them sound the same in loudness, you have to turn up the lower frequencies more and more as you go deeper and deeper. And you don't have to turn them up quite as much when you go to the higher frequencies where our sensitivity is a little bit better than it is for the bass. So in the loudness meters, what we have here is a correction equalization system consisting of two filters. The first of which is a bass roll-off, which is the purple graph on the purple line on the graph, and that approximates our insensitivity to a lower frequency. So the lower in frequency you go in the graph, the less we hear it, and the less sensitive the meter would be using this filter. The pink one there is a high frequency shelving filter, which is designed to approximate our increased sensitivity to higher frequencies, and that's what we feed into our new meter here to make it more accurately show loudness. And when we put this into practice, in the case of a stereo signal, which is what we've been showing examples of here in this presentation, we take the left and the right channels and we run them through these compensation filters called K filters. Then we take an RMS calculation of the loudness, which is what the VU meter does on its design. And in this case, it's a 400 millisecond rise and fall time on the metering. And then we add them together. And that result, if you just stop right there and apply it to a meter, what you get is a basic loudness meter that's an updated version of a VU meter. So that's what we're showing here. On the VU meter, the units of measure is in volume units. But for a loudness meter, because we have this correction here and the 400 millisecond averaging time, what we end up with is a value called loudness units, or LU. Because these meters are not fast, you will lose the ability to know what your peak headroom is by using this basic 400 millisecond averaging meter by itself. So loudness meters typically have a true peak indication on them to show you what the how much headroom you have. And on this meter on the right here, which is one of these new design meters, you see a little red line bouncing up and down at the very top end of the scale. That is the peak value of what's going on to give you an idea of what the headroom is. So if you look on the meter on the right, you see a yellow and green meter, where green is on the lower half and the top half is yellow. That is your 400 millisecond average, which you can think of as the new VU meter, if you will, except this is a loudness meter. So instead of measuring audio in volume units, which is what VU stands for, these new frequency compensated numbers here are referred to as loudness units, or LU. This meter here is the result of a lot of work and research by Bob Katz, taking these standard meters here and turning them into a kind of what I like to think of as an updated VU meter. But it's really accurate in showing you what the relative loudness is between elements. And we can show that here on the next slide here, where we take our same two files that are normalized to minus 24 LUFS, and we run them through this meter. And you can see here that if you watch the green the bar graphs for left and right channels, you see that they're pretty much matching each other with these two songs. The ones that are normalized to minus 24 LUFS, even though they look different visually, once again, they sound the same by ear, and these meters are showing you that. Now, the one thing you can see here is the song on the left has more peaks to it because there's more peaks in there. So you see the little red peak bars moving around more actively than you see on the right, where all the peaks have been removed on that in an attempt to make it sound louder when the song is peak normalized against some other source. And now, in all of the presentations you will see from us here, we're going to be talking about loudness reference levels. When we say this source here is minus 24 LUFS, this one over here is minus 16, this one over here is minus 27 LUFS, whatever. What they're referring to is the integrated loudness, and that comes as a result of using the BS 1770 loudness meter. And there are 3 meters involved with this. And the very first meter you see here is the short-term loudness, which is the 400 millisecond average. And it's the same thing that the meter on the previous slide is showing you, which, again, you can kind of think of as the new VU meter, or in this case, we call it a loudness unit meter, LU meter. The second meter is a slightly longer average of time. It's a 3-second average meter. And that's meant to give you an idea of what your relative loudness is going to be ultimately. That 3-second average gives you a pretty good indication of how the ear is perceiving the loudness of the file in the overall scheme of things. And the meter on the right is the integrated loudness meter, which is an even longer integration time period. Typically, the integrated loudness meter is used to measure the average loudness over the entire length of a media file, whether it's a movie, a song, or whatever. You run it through and it does an infinite averaging across that file until the file ends. And that resulting number is your integrated loudness for that file. And when you're doing file-based delivery, such as songs on the internet and music services, such as Spotify, Apple Music, Amazon, etc., the resulting loudness target that they want you to achieve is the target that is represented by the integrated loudness meter. Now, all of these meters are referenced to 0. So full scale is 0. So when we talk about the loudness unit reference, usually we're talking about them in terms of LUFS, or LUFS, which stands for loudness units full scale, or loudness units reference to full scale, meaning it's a meter like this where it ends at 0 and then goes down from there. You also hear on some of the older documentation the terminology LKFS, which stands for loudness units K weighted full scale. And that's essentially the same thing. It's just LUFS is a newer way of saying LKFS in this case. So there's a quick overview of what we're talking about with loudness here on these presentations and in our more deeper, more technically oriented papers that you can find out here on these resources once again to show you, such as the AES 71 loudness standard. Also, this information is referenced and is explained in further detail on the AES TD 1008 recommendation documents for streaming audio and the new AES 77 streaming audio loudness standard. You can also find out more information on this using the ITU BS 1770-4 and R128 loudness standards, which are the standards all of these are based on. So thank you very much, and we're on to our next presentation. Hope this helps, and have a great day.